Today we're going to solve some systems of nonlinear equations. So, quick little warm-up, we're looking at one that is solving by graphing. So if you look at this quadratic and this linear function, the 2 points that make both of those equations true at the same time are the points -4, 8, and 0, 0. So there are 2 solutions to that system of equations. Solving by graphing is nice if you already have a graph generated and if you only care about the real valued solutions. If you're looking for all solutions, including the non-real complex ones, then a graph is not going to show those to you. Instead, you can use substitution or elimination. So if you look at this one, if you think about substitution, it's definitely doable. I could solve for x or y in the second equation or y nicely in the first equation, but I could also just straight up add them together, and my positive 1y and my negative 1y would give me 0y. I would have to be careful not to combine x squared and x to the first though, because remember they're not like terms. So if I add them together, I'm going to have x squared plus x equals 2. And then I can solve it by getting 0 on one side and factoring, or your favorite other method for solving quadratics. I ended up with x equals -2 and positive 1, but I need my y values that go along with each one of those as well. So I'm going to have to plug both of them back in and see what y values correspond. Make sure you keep track of which x value gives you what y value out, because it's important they're paired correctly. So if x is -2, I'm going to pick that second original equation to plug -2 back in for x and then solve for y. So I end up with y equals positive 2. So if x is -2, y is positive 2. That's one solution point. If x is 1 and I plug it back into that same equation, I get -1 for y. Now I do need to check these in my original equations, both of them, to make sure that they work. I'm not going to actually show you here, but plug them back in and make sure that they do both work. If you look at this one, we've got the equation of a circle and a line. So we're looking for some points where they intersect at without graphing. If you think about elimination, that's not going to work on this one, because if you try to eliminate any variables in the first equation, they're all to the second power, and the second equation, they're all to the first power, so there are no like terms. And even if you did something crazy like multiplying the second equation by x to get x squareds, then you've introduced x into other locations and it's not going to work out with elimination. So we're going to need to do substitution. Let's, in the second equation, since neither one of those are squared, solve for either x or y. I'm going to go for y, and then I'll plug it back into my first equation. So remember, when you do substitute your expression that you get back into that first equation, that you put it in its own set of parentheses, because in this case, we're replacing y that needs to be squared. So when I plug that back in, I'm going to have to make sure I square the quantity 3/4 x plus 1/2. And I'm going to go ahead and, since I do need to make sure that I multiply it times itself every term and use the distributive property, I'm just going to go ahead and write it twice there. And then if you multiply everything together, you're going to get a 9/16 x squared, a 3/8 x, another 3/8 x, and a 1/4. I'm going to combine some like terms while we're at it. That would be 6/8 x or 3/4 x in the middle there. If you add x squared, which is 16 over 16 x squared, to our 9 over 16 x squared, we get 25 x squared over 16. And then I'm going to go ahead and get 0 on one side by subtracting 5. Okay, well, I am not a fan of all those fractions, so if I multiply by my least common multiple of my denominators, I can get rid of all the fractions and turn it into an equivalent equation. You don't have to do this, but I would prefer not to plug all those ugly fractions into the quadratic formula, which is what I think I'm going to go for here with my new equivalent equation. You could possibly factor, but that just looks like it might take a while to get there. Oh, yep, I got a perfect square when I did the values of the radical, so it would have factored, but that's all right. When you get all said and done, you get x equals 2 and 76 over 50, which reduces to 38 over 25. Now I need to plug those back in. So it is much easier if you plug them back into the second equation, the simpler one, than it is if you plug them into the first. If you plug them in the first one, you're actually going to get extraneous solutions that don't work when you check them. So I'm going to substitute back into actually the one that I had rewritten and solved for y, which is going to give me x equals 2, y equals -1. And when I plug in my 38 over 25 into that same equation, I'm going to get a corresponding y value of 41 over 25. And if you check them, they do both work in the originals. Okay, you always wanted a challenge, right? So this one, if you look at it, if I try to do substitution, there's not anything really that's an easy variable to solve for and get by itself. So I am going to do elimination, even though that might not look like it's going to get us anywhere either. But I'm going to multiply the bottom equation by -1, and then look at what happens. It's not going to be perfect, but my x squareds eliminate and my y squareds eliminate. I still have that 2xy term that's now equal to 30. So there's still two variables, but I'm actually going to pick either x or y. I'm going for y and solve that one for a variable. And then after I reduce it, substitute that back in. So it's a combo. I did elimination to get something that was easier to solve for a variable, and then I'm doing substitution. I'm going to plug that y value back into my second equation, and then make sure you don't forget to square it. If you square 15 over x, you're going to get 225 over x squared equals 16. And there's a couple different ways that you could do this. You could get a common denominator by multiplying x squared by x squared over x squared, which is actually, I think, what I'm going to do here. Or you could multiply the whole equation through by x squared. So I got a common denominator and then wrote it as a single fraction. And now, if my left-hand side's all over x squared, I'm going to undo that division by multiplying both sides by x squared. So we're going to end up with x to the fourth minus 225 equals -16x squared. And then I am going to add my 16x squared to get 0 on one side. And we talked about earlier in this class that we could factor that or use some different approaches to solve it because it's in sort of a quadratic type form. So I'm going to factor it into x squared plus 25 and x squared minus 9. Multiply it back together just to check yourself. That does equal the original. And then if you set each of your factors equal to 0, you end up adding 9, taking the square root. Don't forget that gives you positive and -3. And on my other factor, I end up with positive and -5i. So this is one where if you solved it by graphing, you would be missing some solutions. I do need to plug all 4 of those back in. So let's do if x equals 3. You can save yourself some work here by picking the easiest place to plug it back into. So I had y equals 15 over x. So let's plug it back in there. So 15 over 3 is a y value of 5. So one potential solution is 3, 5. If I plug -3 back in, 15 over -3 is going to get me -5. I did already check all these in advance, by the way. They do all work. If you are checking by hand, make sure when you plug something with I back in that you remember I squared is equal to -1. If you plug 5i in to see what your y value is, you get 15 over 5i, which you could reduce your 15 over 5 to 3 over i. And then remember, if you don't want an I left in the denominator, multiply by I over I. And then in your denominator, I squared is equal to -1, so you get -3i. And then my last value that I got for x was my -5i, which is going to go pretty similarly here. Plugging it back in is going to give you a -3 over I, and then multiplying by I over I, you're going to end up with just a positive 3i. So you have 4 solutions to the system of equations.